Hi everyone, in this video we are going to be solving log equations. Before we were solving exponential equations, so now we're solving log equations. Some of this you already know how to do, and some of it will be just a little bit new, but because you know what logs are and the log definition and the log properties, we're gonna be able to use all those to help us solve, and it won't be so bad. Alright, so the first type I'm going to show you is just how to use the definition, and there is another way to do this one, so I'm going to show you both methods, but the using of the definition of a log is something that you already know and you're already comfortable with, so you might want to just continue to use that. Alright, so here's the first example. Log base 5 of 3x plus 1 equals 2. So I will solve it both ways so that you see both ways. The first way is the way that you already know. So this is method 1, and it's using the log definition. Okay, so using the log definition, you would just rewrite this using the log definition, so rewriting it as an exponential. So that means we would have 5 squared equals 3x plus 1, and we would just solve this. So 5 squared is 25. 25 equals 3x plus 1. Subtract 1, we get 24 equals 3x. Divide by 3, and we get x equals 8. For log equations, you always have to check your answer, because it could be that you get something that's extraneous. And you should just check your answers all the time anyway. But if we plug this back in, so here's my check. We would have log base 5 of 3 times 8 plus 1. Does that equal 2? Okay, so we'll have log base 5 of, that'd be 24 plus 1, which is 25, equals 2. And then if we just think about this, 5 squared is 25, so that is correct. Okay, the other method that people use is called to exponentiate. All right, so this is method 2, exponentiate. Okay, so we'll start off with just the log base 5 of 3x plus 1 equals 2. So that's the equation. All right, when we exponentiate, that means we raise each side to the base that is equivalent to the base of the log. So that means I'm going to do 5 to the log base 5 of 3x plus 1 equals 5 squared. So I took this side and put it as the exponent base 5, and I took this side and put it as the exponent base 5. The reason why I'm doing this is because now 5 to the log base 5 inverts itself. That's an inverse property of logs. So that means that I just have 3x plus 1, right? That was a property that we had in our other video, in the exponential video. And on the other side, I just have 25. All right, then I subtract both sides by 1. 3x equals 24. Divide by 3, and I get x equals 8. So both ways we get x equals 8. I already checked it, so I know it's correct. It's up to you which method you want to use. I know if you're more comfortable with the log definition, keep using it. If you would like to exponentiate, do it that way. So you do have to match the base though. So I used 5 because that was the base of the log. That's the only way you could use the inverse property. Invert it, and get what you're taking the log of. Okay, so I'll do one more like this, and then we'll go to another type. Okay, so second example, we have 20 natural log of 0.2x equals 30. Okay. The only reason why I'm doing this example is to show you that you need to get the log by itself to use either method. So here, if I wanted to use the log definition, if I wanted to use the exponentiate, method, either one, I would have to first divide by 20 to get the natural log of 0.2 to the x equals 3/2 to get this by itself. Now that that's by itself, I have the option. Okay, so I can either use the log definition or I could exponentiate. Up to you. I'll exponentiate just because you haven't seen that too often yet and you have already seen the log definition a few times. All right, so I'm going to do e to the natural log of 0.2x equals e to the 3/2. Notice that I'm using e to match the base. The base of the natural log is e. All right, so that's going to invert itself and we'll be left with 0.2x equals e to the 3/2. And we still want to get x by itself, so I'm going to divide by 0.2 and I get x equals 22.408 from our calculators. And like I said before, we will have to substitute this back in to make sure that it's correct. So that's going to be my last step here, is my check. All right, so I'm going to have 20 times the natural log of 0.2 times 22.408. Does that equal 30? And this is just something I'm going to check on my calculator since I really don't, know what the natural log of that value is in my head. So I'm just typing it into my calculator, make sure that I get the other side or at least very close to it, because there will be some rounding, and I got 30 for this actually because I used the whole number. So we're good. So whenever you get an equation that has a single log, you're going to want to make sure that that single log is by itself, and if it's not, you get it by itself, and then you continue solving whichever way you want, either by exponentiating or by using the log definition. Okay, so now we're going to look at what happens when you have a log on both sides. So for this one, we need a property. And this is kind of a property that you sort of know already. So this property says that for positive numbers, b, x, and y, where b cannot equal 1, the log base a of x equals the log base a of y if and only if x equals y. So this is something we already kind of knew. We talked about it a little bit in our log properties. And this property is going to help us solve when we have two logs of the same base equal to each other. So for example, when we have log base 3 of 5x minus 1 equals log base 3 of x plus 7. Okay, because these are the same base, we know from this property that 5x minus 1 must equal x plus 7 for these two things to be equal. So you just set what you're taking the logs of equal to each other and solve. So I would subtract x from both sides. I would get 4x minus 1 equals 7. Add 1, 4x equals 8. And then divide by 4, and x equals 2. As always, we're going to check. All right, so we have log base 3 of 5 times 2 minus 1 has to equal log base 3 of 2 plus 7. Okay, so this is going to be log base 3, 10 minus 1 is 9, equals log base 3 of 2 plus 7, which is also 9. Those two things have to be equal, so we're good. Okay, so anytime you have a log with the same base equal to each other, and it's just those two logs being equal to each other, you just set what you're taking the logs of equal to each other, solve for x, and as always, always check. All right, we have one last type. the last type is going to be one where we have to use our properties. So here's our last example. We have log base 10 of 5x plus log base 10 of x minus 1 equals 2. So we're using the common log here. All right, so I don't have a single log like on the left side of the equation. I have two logs being added together, but I know that when we add two logs together, that's the same as the product property of logs, meaning I can put it together as one log being multiplied. Okay, and once I see this, then I can simplify a bit more, right? What I'm taking the log of can be 5x squared minus 5x equals 2. Okay, so once again, it's up to us if we want to use the log definition or if we want to exponentiate and raise it to use that same base of 10 and raise it. I'll do the log definition here since the other one we did exponentiate. So that means I'm going to rewrite using the definition here. So I'm going to have 10 squared equals 5x squared minus 5x. 10 squared is 100, so I have 100 equals 5x squared minus 5x. And then I'm going to get everything on one side since this is quadratic. So I'm going to subtract 100 from both sides. And then I have 0 equals 5x squared minus 5x minus 100. And from here I'm going to have to factor. This is factorable. So it factors into 5x plus 20 times x minus 5. So then we use the zero product property, set both equal to 0, and I have 5x plus 20 equals 0, and x minus 5 equals 0. So for this one, I subtract 20, get 5x equals negative 20, divide by 5, and you get x equals negative 4. And then for this other one, you add 5 to both sides, and you get x equals 5. And remember that for all of these equations, we have to check our answers, especially now that we know we could get something that's extraneous. All right, so I'm going to check first the x equals negative 4. So I'm going to have log base 10 of 5 times negative 4 plus log base 10 of negative 4 minus 1 equals 2. So that's log base 10 of negative 20 plus log base 10 of negative 5. Does that equal 2? Well, it can't. So right here, I already know to stop because I can't take a log of a negative, right? That's part of the definition of a log. It should make sense also, like if I looked at this one, the definition of this one would be 10 to what power equals negative 20. Well, that's never going to happen. You're never going to be able to raise 10 to a power and get a negative. All right, so any power, even if it was a negative exponent, we would get, for instance, 1/10 if it was negative 1 for the exponent. So that's never going to happen. So I could already stop. So here I know that negative 4 is extraneous. So that means that I can cross that one out. I still have to check the other one because I don't know if that one's going to work. It could be that both of them are extraneous and that there is no solution to the equation. So let me check this one. Log base 10 of 5 times 5 plus log base 10 of 5 minus 1, does that equal 2? So that's going to be log base 10 of 25 plus log base 10 of 4, does that equal 2? Well, let me use a property here. So this is going to really be log base 10 of 100. Does that equal 2? Since they're being added, I can multiply, write it as a single log. And then this is 10 squared equals 100. That does work. So 5 is a solution. Okay, so if I had an equation that instead had this on the other side, let's say, I would bring it over. You want all the logs to be on one side, and then you could rewrite it as a single log and solve from there. All right, so now with these examples, you should be able to do the problems that are assigned, and we will review them during our next class. All right, thanks for watching, everyone.